All right. What is up, peeps? This is James, former Ergonomics and Brakes lead and alumni from Dallas Formula Racing, aka UT Dallas's Formula SAE team. Graduated in 2024. So this is the second installment in our series covering the course titled Ergonomics and Automotive Design. This is my take on this course by this professor here, and sort of me making the material more applicable to SAE. So you can there's a link to the original course, and it's actually the link has changed now. It's not the one you see on the screen here. I'll put it in the description below. But there are videos you can watch, original videos. But this is just kind of a condensed version and more tailored to SAE applications. So, second installment in the series. Let's get right into it. So the next section of the course and the subject of this entire video is going to be driver information acquisition and processing. So what are the types of information a driver needs? Well, there are 5 different sensory channels from which the driver's brain gets information. The first is visual channel. So vision is arguably the most important sense in driving. The driver is pretty much always looking at the road, so it's important to keep critical displays close to their line of sight so that they can avoid looking away for too long. If they got to glance at their dash, they only have to for a second. So making sure things are very close to their line of sight. Main receptors here are the rods and cones inside of your eyes. As you can see, image here. So the rods are detecting light and the cones are detecting color and detail. So the main key info that you're getting here is things like a track layout, cones, barriers, shift lights if you have any, and also depth perception in the sense that which is essentially the ability to perceive and judge the distance between objects. So that helps with when a driver is going into a corner and they can judge how much they need to brake and turn before going into the corner. So that's the key info that you're getting from this sensory channel. The next sensory channel is auditory, from the ears or cochlea. So, and let me turn this down. So your ears, the hair cells in the cochlea of your ear are detecting sound. And so sounds tell the driver what's happening without looking. So things like engine revving, as you can hear in the video, you can hear the engine revving, and you can kind of tell when the engine is redlining or reaching its max RPM, and that kind of tells the driver without looking or even looking at the shift light if they have one, when to shift. The other thing you can hear is the tires squealing, which tells you that you're either understeering or oversteering, in other words, slipping. So traction limits. And the other thing that you may have, maybe some teams might have, is a team radio of some kind, which kind of clues you into strategy. If you're on a track, like on the course, maybe at competition, they tell you, maybe you have someone calling out on the radio, hey, you have a strict hairpin turn coming up or something. Maybe have a way of tracking where they are on the track, and then are able to have someone be kind of a call out person. So those are the main things. Key info. Team radio is less common, but it's still something possible. So yeah. The next sensory channel is tactile, which is through the skin corpuscles. So mainly there are 2 receptors for tactile sensory channel. It's the Meissner that's depicted up here, and the Pacinian corpuscles. So think of the Meissners as the uh, more texture sensors, and the Pacinians as more deep impact and vibration sensors. Together they kind of give the driver a complete tactile map. The Meissner is kind of more fine textures and lighter pressures, and then Pacinian corpuscles are more deeper pressures and more it's like force feedback. So in essence, the key info that you're getting here is uh, grip of your steering wheel, your pedals, your shift knob, and any kind of texture. So that's what this sensory channel deals with. The next sensory channel is olfactory, or from the nose olfactory bulb. So this is uh, less racing and more kind of a safety thing. So your olfactory bulb receptors are detecting any kind of smell. So your nose can give you early warning signs of stuff. For instance, if you smell like a sharp, pungent chemical odor that's usually described as kind of a sweet odor, sweet chemical odor, that's usually means that it's like a fuel smell, so which could mean there's a potential leak, which obviously is a safety concern. So that'll tell you to check for leaks before it becomes dangerous. Or if you smell smoke or burning clutch smell people describe as kind of a combo of chemical and burnt rubber and hot metal smell. It could indicate that the clutch is slipping. If you smell a smoky smell, it could indicate that the car might be overheating. Uh, or that there's possibly, yeah. So not really mainly for racing, but it's more a safety thing. But anyways, when your olfactory bulb receptors can prevent big problems, essentially safety concerns. And the final sensory channel is the kinesthetic. So the kinesthetic, your body tells you how the car is moving without even looking. How? Two things. There is proprioception, which is mainly your muscles and joints, which feel seat forces and how more so forces, like when you impact side of the car, things like that. Your body, your actual physical forces. Vestibular input or the vestibular hair cells in the inner ear, which kind of sense tilt, rotation, balance, and orientation. So these kind of together both give you an idea of how the car is behaving in corners, braking, acceleration. You can see in this video here, you can feel. Uh, this is a test people do for torquiness in their car. Um, you can see this kid is pressed up right against his seat. That's an example of both your proprioceptor and vestibular hair cells detecting movement. If you close your eyes, you would know that the car is launching forward very rapidly. And so that's what I'm kind of that we're kind of demonstrating here. And then this chart is also kind of showing you this is an accelerometer which um, tells you where the G's are focused laterally or if we're accelerating or braking. So obviously, if you brake, your G's are gonna kind of lurch forward. So that's mainly what your vestibular hair cells are detecting, that those G forces for both the entire kinesthetic sensory channels detecting. So G forces, um, orientation, pitch. So that's pretty much everything that this sensory channel covers. Oops. So um, overall, we have these 5 sensory channels, and each of them gives the driver's brain info. and each tells the driver something different about their environment, car and track. So, and these are the receptors for each of them, and this is what each of those receptors tells the driver. So visual sensory channel, you're getting color, form, size, and depth perception. Auditory, you're getting your um, pitch, loudness, tactile is texture, olfactory is smell, kinesthetic, you got your balance, orientation, and motion. So just kind of review, this is what each of the sensory channels, what kind of info it gives the driver. So what's the difference between sensation and perception? Well, there is some physical stimulus, like say the tires are squealing because there's a lot of friction between the ground and the tire. Um, there's a physical stimulus, and then there's a neural signal that your brain picks up, which is loud squealing tire sound. Uh, so your sensory channel, your auditory sensory channel, is picking up the signal, and then your brain later interprets that signal, or rather understands it as recognizing loss of traction. So that's the difference between sensation and perception. Sensation is the detecting of the signal or the physical stimulus, and then perception is how you perceive, understand, or interpret it. Now, on a more detailed and larger scale, we have the human information processing model, which shows this process broken down step by step. So first you have your physical stimulus, some sort of sound. We'll call it tire squealing. That's your physical stimuli. Then your whatever sensory channel, whether it be touch, auditory, visual, in this case it's visual, picks up a signal, and the squealing tire signal, and that then gets sent to your perceptual processor. So the perceptual processor is what detects the sensory info given, and then after the info is detected, it is interpreted by the cognitive processor, and the cognitive processor also makes decisions. And after both of these steps, um, these things get stored into your working memory and then long-term memory, and then working memory is always pulling from long-term memory consistently. That's why it's kind of like a loop here. I don't know. Don't ask me to go too in detail on how this works, but essentially, this is always a constant loop. So after perceptual processor, you're detecting info, and then after interpreting and making a decision, then there's some motor response. So there's an executed physical response, which overall results in a motor response. So this is the process step by step on how the driver processes info. And this all happens in 3/10 of a second. Perceptual processor, 10th of a second. Each of these processors, tenths of a second. So it happens extremely quickly. So there are different categories of attention. The first is focused or sustained attention. And essentially it's maintaining focus on one task over time. So if a task requires long focus, like for instance, following the racing line through a long corner, as you can see here, the driver's focusing on the left screen is showing kind of what improper eyesight, and the right side is demonstrating proper eyesight. So entering a corner, you want to look at your exit path rather than the corner itself, or apex they call it. You want to look at where you're exiting, where you want the car to go. And so that's what the driver is focusing on in this video here. So that's an example of a focused, sustained attention. They're just focusing on this one thing and looking at their exit path. And so the takeaway here is that, from an engineering standpoint, is that controls and displays have to be intuitive and not require prolonged glances, because if the driver's really trying to sustain their attention on looking at their exit path, they don't want to be glancing at they don't want to have to look at their dash for too long, and so you have to keep it close to their line of sight so that they can just quickly glance. So basically, keep critical info in the driver's natural line of sight to avoid breaking their focus is the takeaway here. Second category of attention is selective attention, where essentially the driver's focusing on relevant info while ignoring distractions. So an example would be paying attention to cones on the track or the track itself while ignoring crowd noise or dashboard alerts that aren't relevant at the moment. So essentially the takeaway here is reduce unnecessary visual and auditory clutter and prioritize alerts, if you have any, by importance. And then the other thing is using sensory cues for critical warnings. An example of a sensory cue is essentially giving the driver info from two sensory channels rather than one. What's an example of that? So we talked about the squealing tire sound. Squealing tire sound is mainly picked up from the auditory sensory channel. Adding a sensory cue, if you add a sensory cue, like for instance, instead of them just hearing and perceiving that as, oh, I'm losing traction, you can also add a sensory cue that shows a dashboard display that pops up that shows a traction symbol. Oh, you're losing traction. So what's that doing? It's providing two sensory channels rather than one for the same thing. And what does that do for the driver? Well, that actually reduces the amount of work that their brain has to do before realizing they're losing traction. So you're essentially reducing the time to execute a motor response. So instead of 0.3 of a second, maybe it might be 2.5 of a second. So that's the idea here. You're trying to reduce the mental workload on the driver because they have more than one task that they're focusing on, right? Selective attention. They're trying to block out all background noise and focus on what they're doing. So third category of attention is alternating attention. Alternating attention essentially means that they're switching focus between two tasks. So an example would be if they're entering a corner and they're quickly checking their shift light to see if they need to shift yet while maintaining correct steering through that corner. So drivers often switch between different tasks. It could be, switching between looking at the rev lights, looking at the apex, or shifting gears. So the takeaway here is that ensure quick glance usability of instruments and controls, so switching attention doesn't slow reaction or induce errors, kind of like what we discussed in the previous two slides. And so final category of attention is distributed or divided or distributed attention. And what this essentially means is that the driver's handling multiple tasks at the same time. So drivers are also always handling multiple inputs simultaneously. Is what this is kind of demonstrating. I mean, you have them paying attention to the sounds that the car is making visually. They're looking at the corner, they're listening to their tires squealing, they're listening to their revs, they're also looking at their rev lights. And so essentially the takeaway from this is you got to design the cockpit ergonomically, your dash, you got to design the car in general ergonomically so that simultaneous tasks don't overload the driver's cognitive capacity. So you got to provide proper tactile, auditory, visual feedback to ensure multitasking is manageable. Things like adding more sensory cues, like the rev lights, for instance. Those are a sensory cue for shifting gears. So that's providing a visual where they already have an auditory sensory channel where they know to shift, hearing the engine. you're giving them a visual here. Same with maybe losing traction if you have the traction control light. So that's kind of the idea here. So to kind of review, for focused, sustained attention, uh, focused attention keeps the driver on a single important task, like perfect line through a corner. Selective attention helps the driver ignore irrelevant distractions like fans or audits or dashboard notifications that aren't relevant at the moment. Alternating attention allows the driver to quickly shift their focus, like glancing at the red lights, then back to the apex. And then divided attention is pretty much the ultimate driving skill. Drivers juggling multiple sensory inputs and cockpit controls without slowing down are very, very skilled. So, overall takeaway, proper cockpit design and vehicle design and sensory feedback reduce the mental workload on the driver and lets them focus where it matters most. So, last section of this video, types of human errors. In driving, mistakes happen all the time. Understanding the different types of mistakes helps us as ergonomics engineers design safer cars and better cockpits. Errors and mistakes affect the decision making, reaction time, and performance. And so there are 11 main types. The first we'll go over is detection error. So detection error is essentially when the driver fails to notice a signal or cue. It could be missing a yellow flag if there's one on the track, or it could be not seeing the shift light, or not hearing something. So they fail to pick up a signal of some kind. So critical takeaway here is make critical signals bright, clear, and visible and in the driver's line of sight to help avoid this kind of error. Second type of error is a discrimination error, which is essentially when the driver confuses similar signals. An example would be if for some reason the driver mistakes the oil pressure light for like an check engine light for some reason. So the takeaway here is use distinct shapes, colors, and or positions to reduce confusion. So you can see here that each of these different symbols are colored differently, shaped differently, and that's kind of the takeaway here. Interpretation error. So an interpretation error is essentially the driver notices the signal, but they misunderstand what it means. Example would be hearing the squealing tire sound. I'll keep using that example. And thinking it's understeer when it's actually oversteer. So it would be wise to provide feedback, visual, tactile, and auditory, to clearly indicate the meaning. So maybe adding a traction symbol for understeer and one specifically for oversteer. Those kind of things. So the next type of human error is omission error, which is essentially when the driver forgets a required step or action. An example would be is that they forget to engage the clutch before shifting, which will cause them to miss shift or jerky, causing a missed or jerky gear change, which is no bueno. So the takeaway is provide reminders if you can, or some sort of ergonomic feedback that ensures that they don't miss these kind of steps. Another example would be if like there's a startup procedure of some kind. Like for instance, on our car, we had 4 switches that we had to flip in a specific order before starting the car. And so if you have things like that, make sure that they're set up in such a way like they're set up from left to right. Like you have to go from left to right to flip the switches and then click a button. That's the kind of thing you can do to avoid this type of error, so that they don't forget to flip one of those switches. Commission error. So commission error is essentially when the driver performs an added, extra, or unnecessary action. So, an example would be if they were for some reason overcorrecting the steering when the car is already stable. So, they're essentially adding an extra input that wasn't needed. So, the takeaway is design controls to minimize these unnecessary inputs, ensure drivers can make precise actions without accidentally overcompensating, is the takeaway here. So substitution error. Substitution error is essentially when the driver performs the wrong action instead of the correct one. So they performed action at the correct time, but it was the wrong action. So example would be if they pressed the brake pedal instead of the clutch pedal when they were shifting, which would be really bad. So takeaway is controls should be clearly separated and intuitive to prevent accidental substitution. And in the case of the pedals, why do you think each of these petals are shaped different? It's actually to be able to distinguish between them, most likely, and also likely designed for what type of force they'll be receiving as well. Uh, but so two birds with one stone. There's how much force that these different petals require, and also distinctive shapes so that you can tell the difference between them. And also providing proper spacing between petals is necessary as well, so that they're not super close that you might mistake them for each other. So that's kind of the takeaway here. So reversal error. Essentially, the correct action was performed, but in the wrong direction or sequence. An example would be that you upshifted instead of downshifted when entering a tight corner. So the takeaway is gear lever design and visual cues should minimize directional confusion. And this kind of goes back into what I was talking about earlier as well. If you have a certain startup procedure and you have certain switches that have to be flipped in a sequential order, a specific order, set them up so that they're placed left to right in a perfect order, so the driver intuitively knows, okay, I go from left to right, switch, and press this button. So that's the takeaway for trying to avoid this type of error. Inadequate response error. So inadequate response error is essentially when the action that is taken it's taken at the right time and everything, and it's the right action, but it is too weak or too strong. An example would be braking too lightly or too heavily in a skid pad turn and maybe overshooting a cone or something. So the takeaway is the feedback from pedals and seat forces or whatever ergonomic component should help the driver indicate the proper effort needed. Or an example would be ABS systems, automatic braking systems. ABS systems are meant to help the driver brake at the proper frequency, because cars without ABS system, you kind of have to pump the brakes a little bit in order to brake properly. So an automated brake, an ABS system is an example of accounting for this, preventing this sort of inadequate response error. So it's helping the driver, it makes their job easier, and keeps them safer. Legibility error. So a legibility error is essentially when the driver misreads unclear or illegible or cluttered info. So example is if the driver is misreading a super small, tiny digital readout, or even misreading it because there's a lot of vibration and it's just unclear whenever the car is, hitting heavy bumps, they can't even read it. So the takeaway is displays of any kind should be large, high contrast, and vibration resistant, in the sense that even if there are intense vibrations, you can still see the display very clearly, whatever symbol is being displayed. So now we have recovered error. Recovered error is essentially when the driver makes a mistake but corrects for it in time. Example would be that they turned too early during a turn, but they correct it before hitting a barrier or spinning out or spinning off the track. So takeaway is cockpit and control should always allow for quick recovery and not trap the driver in any kind of way. So that's kind of a given. The next is unrecovered error, which is essentially when the driver made a mistake that wasn't corrected and ultimately leads to total failure. Example, driver crashes. As you can see in this video, they kind of spin out and lose control and they hit the wall. Not too bad. Oh, I don't know if their rear axle is damaged actually. But this kind of highlights the importance of, well, one, driver training, and also uh, quick recovery responses and implementing clear. Oh man, this guy's really pissed off. I feel kind of bad. But quick recovery responses and clear feedback systems to help prevent small mistakes like this from escalating. So there's only so much the driver can do with what skill they have. So you have to help provide an ergonomic systems that help the driver do well regardless of their skill. So these are the 11 types of human errors. So just as kind of a review, detection error is when the driver fails to notice a signal. So make sure that critical and visual auditory signals are prominent, easy to read, easy to hear. Discrimination error is when the driver confuses similar signals. So be sure to use distinct colors, positions, icons on dashboard displays if you have any. Interpretation error is the driver notices the signal but misinterprets its meaning. So feedback should always clearly indicate vehicle behavior. So if you hear a tire squeal and think it's understeer when it's actually oversteer, provide a dashboard display that tells the difference between two. Help the driver less mental workload. Omission error is when the driver forgets required action, forgetting to enable clutch before shifting, things like that. So provide reminders or interlocks for critical controls so that the driver does not omit any required steps. Commission error, driver performs an extra unnecessary action, so the takeaways avoid unnecessary controls and ensure critical actions are very distinct. Substitution error, driver performs a wrong action instead of the correct one. So controls got to be intuitively separated and labeled to prevent these substitution mistakes. Then you have your reversal error, which is similar. So it's the correct action, but in the wrong direction or sequence. So make sure that whatever controls you have, whether it be your gearbox or paddle design or shifter design, minimize directional confusion. So if you do have a shifter, make sure it's clear which direction the different gears are in, or maybe implement a quick shifter, which is a lot simpler. It's just one direction, go upshift the next gear. Make sure it's labeled so that the drivers know. And then inadequate response error is, driver's action is too weak or too strong. So make sure there's proper control feedback, whether it be the pedals or even seat and steering forces, help the driver know how much effort to apply. Anything that helps the driver apply the correct amount of effort. Legibility error. So you got to make sure that so the driver misreads unclear dashboard info. Display should be large, high contrast, and easy to read at a glance. And then recovered error. The driver makes a mistake but corrects it in time. So cockpit and car setup should allow for quick error recovery, essentially. So ergonomics should allow the driver to recover very quickly. And then unrecovered error, which is kind of discussing the same thing. It's when a mistake was made but couldn't be corrected, which led to ultimate failure. So takeaway is high risk actions should have design safeguards and not rely only on driver's skill. So to kind of sum up, we discussed some examples. They all directly tie into driving and specifically FSAE. So takeaway is ergonomic engineers have to optimize their cockpit layout controls and ergonomic feedback systems to help the driver perform optimally. And driver training also plays a role in this as well, in reducing errors, improving lap times, and safety. So that's pretty much it for today's video, guys. I really hope you enjoyed it. If you want me to continue this series, please let me know. You can comment below. And just thank you for your time, and check out the original course if you are interested. On NPTEL is the organization that made the content in this course. So this is just my presentation of the content, just presenting it differently. Thank you all again.